Good afternoon or good morning, depending on where you are in the world, and welcome to today's webinar entitled AI and ML Ready Modern Data Platforms. If you want to ask any questions throughout today's session, please feel free to post questions in the chat pane. My name is John Miller, and I'm joined by my colleague Lauren. We're both data analytics and BI consultants for Thorogood. I've included our emails and LinkedIn accounts, and would encourage you to reach out with any questions, or if you just want to connect, feel free to reach out to us. So today, Lauren will be talking about how you can structure your data platform to be prepared for using AI and ML solutions. Before we get into that, I'm going to give some background on the cloud and machine learning, just to make sure everyone has a good foundation before jumping into the application. Just to start out here, I'm going to talk about Thorogood and who we are and what. In short, we help our customers make sense of their data. We're an independent and specialist data and analytics company with a focus on data engineering, data science, and data visualization. Our approach is rooted in understanding business goals and using the capabilities of technology to meet these goals, so our customers and their business objectives are at the forefront of our approach. We're a global company with offices and consultants in Asia, Europe, and the Americas. And we offer a full range of services when it comes to data and analytics. These include data and technology strategies and roadmaps, end-to-end implementation of cloud solutions, user empowerment trainings, and analytics services. We do have strong experience in a number of industries. Some industries that we find that are typically data-rich are banking, insurance, pharmaceuticals, and consumer packaged goods. But we do work with customers in many other industries as well. I've listed just a sampling of some of the companies that we've worked with. In terms of technologies that we work with, we are an independent consulting firm, as I mentioned, meaning that we don't work with just one specific technology. We do, however, work and partner with many of the key players in the market in order to provide our clients with the solution that best suits their needs. It's not necessarily just Microsoft or just Amazon. We really try and take into consideration the needs of the client when coming up with a solution. So next, I'll go over some cloud computing basics. As a refresher for everyone, we'll just start with a simple definition. So cloud computing is the use of resources that are located and managed remotely, offering computing and storage to users on demand. So leveraging cloud technologies is now ubiquitous across large data-focused companies. I'm sure many of you are already using cloud technologies within your daily lives. So essentially, the cloud enables business intelligence tools to be delivered at a low cost without additional infrastructure or maintenance, since they're hosted on external shared servers that are accessed via the internet. These cloud tools are split into 3 buckets of varying management levels. At one end, we have infrastructure as a service, which allows the end user to retain the most control. Examples of these are virtual machines or storage accounts. Essentially, all you're asking a cloud provider for is a server to host the machine. Next, we have platform as a service. It still allows the user to manage the applications, data, and the access, but the cloud provider is responsible for the rest. An example here would be a cloud-hosted database. Finally, at the other end of the spectrum is software as a service. This lets the cloud provider manage all aspects except for data and access. So if you use Salesforce or even your Gmail accounts, you're using a software as a service tool, where the cloud provider pretty much handles everything and you just interact with it and upload data. Services can be used singularly or together in any combination of data storage, data analytics, reporting tools, and different applications across different vendors. As you can imagine, there are many different cloud tools available in the market today. You can choose cloud tools with varying degrees of service, with flexible, customizable options within each, depending on your business needs. Cloud providers today taking up the biggest share of the market are Microsoft's Azure platform, Amazon AWS platform, and the Google Cloud platform. But it is a rapidly growing area, and the other companies listed here, and even those not listed here, are continually improving and competing for market share. Adopting the cloud is no longer solely about economics and agility, though it provides much of the foundation. It's becoming enterprises' most critical and dependable source of sustained technology innovations. As innovative technologies like machine learning algorithms, artificial intelligence, blockchain, and Internet of Things are available for everyone through the cloud, digital transformation drives the need for organizations to develop new cloud-native applications to create immersive experiences for their customers. When applying cloud economics to data and analytics, it's important to think about defining governance guidelines which align with your cloud strategy and your organization's direction across business and IT. Some key aspects of the strategy are monitoring your utilization, making sure you're using DevOps, upskilling both IT and business users, identifying opportunities to leverage the cloud across your business, and then promoting that modern data platform that Lauren will get into later. So now that we have an understanding of cloud computing, let's get into machine learning. How does machine learning work? What are some of the key steps in a machine learning initiative? So obviously, we're going to start with some data. So you have your data. Your data is separated into two parts. There's features and there's labels. Features are any part of the data that could be a contributing factor to the outcome that you're trying to predict. That outcome is what you would call your label or quantity. The different names depend on if you're predicting a label that groups data into predefined buckets or a quantity that's predicting a certain number. During development, we'll initially split the data randomly into a training data set and a test data set. We can select which features we want to use, giving us the ability to include or exclude certain fields from the model. These can then be updated later when iterating and improving on the model. We'll then feed our model the training data so that it can form an understanding of how the selected features impact and correlate to the label/quantity. Once trained, we'll then run our test data through this trained model to understand how accurate the model is. We can see the results of the evaluation from our model alongside with the actual values from the test data. Looking at the evaluation can then give us ideas on how to improve the model so they can continuously refine using different features or different algorithms, just so you can get your model to the point that it's ready for production. Ultimately, we'll look to industrialize our model through the process of MLOps, whereby we automate the feeding of data into the model and even execution of the model, so then it can be ready for the business to use in decision making. Selecting the right type of model for your use case is a very important step. While there are many different algorithms that can be selected, there are just two main types of models. There's classification and regression. The classification will try to determine which bucket a record belongs based on the features that are selected. The evaluation of the model will return a confusion matrix that will give you insight on the accuracy and precision of your model. Regression, on the other hand, is used when you're trying to predict a specific quantity, so it'll try and fit the regression here. Here's an example of linear regression that just tries to fit a line to the data so it can be used to predict the quantity. So how do you break down a data science project lifecycle? Well, the approach that we have found successful with our clients is based on the cross-industry standard process for data mining, or CRISP-DM for short. We start by combining the business understanding with the data understanding. Then from there, we rapidly iterate through different scenarios with a constant feedback loop to help inform that decision making. After we have a clear picture, we'll then move into preparing the data sources through different ETL activities, building models on top of cleansed data, and things like that. Again, this process happens rapidly by leveraging cloud tools that let us test multiple models easily. Feedback from the evaluation step can then inform our data engineering. Do we need to change what features we're using in the model? Do we need to update the model's algorithm or any other parameters that we can control? Once the model has been tested and validated, it's then time to deploy it so that it can be tested in real-life scenarios. While a model is deployed, it's important to monitor the performance to ensure that the outputs of the model remain in the desired accuracy parameters. And while it's not drawn here, any findings should be fed back into the process to update the model as required. So some of the challenges that many people face when using ML is trying to scale it beyond ad hoc experimentations. Building a tool that is trusted by the business is the ultimate goal, and when trying to scale, companies can face many issues. Some of these are scalability, so how would you branch out to other countries, different channels and retailers, alignment from senior leadership on data science governance, reliability, does the business actually trust your model, resiliency and reproducibility, and accuracy issues with the model. On top of these, it's hard to quantify or know if an experiment will be useful up front and relying on data scientists to manage supporting these models once productionized reduces their time spent on innovating new models or improving them. MLOps, which is a set of principles for operationalizing machine learning, helps to address these by building a framework of auditability, monitoring, and responsiveness. It also empowers data scientists through automation, scalability, and reproducibility of machine learning solutions to allow them to focus on those higher value activities of innovating new ML models and new experiments. We do have a 3-part MLOps series that dives deeper into the benefits of MLOps. If you're keen to learn more, you can find that on our website, thorogood.com, or on our YouTube page. So I'll now pass it over to Lauren to talk about modern data platforms.
All right, thank you, John. So now that we've introduced cloud and machine learning, let's get into talking about a data platform that supports these two ideas. So I'll start with a definition. A modern data platform is a set of best practices that allow you to get the most out of your data with the least amount of platform management. Here are some characteristics that a modern data platform has. So first, it is scalable, both with its audience and with its data. It needs to support a variety of use cases, users, and usage patterns. This means having the ability to do ETL and transformations for data engineering, queries for data analysis, and experimentation and ML for data science. A modern data platform also needs to be scalable with its data. It can ingest a high volume of data from a variety of data sources at high velocity. A cloud model is necessary for a modern data platform to operate at the scale needed for current business use cases. Secondly, a modern data platform is self-service. It supports the idea of data democratization, enabling everyone in an organization to comfortably work with data. There are a few key ideas that lead to data democratization. There's data discoverability, easily finding data that you're looking for. Data federation, combining data from multiple places into one data model. And then data virtualization, retrieving and manipulating data without knowing its format or where it's stored. One specific benefit of data virtualization is that it allows analytics at higher speed and lower cost. So these 3 practices lead to democratized data, and data democratization results in the enablement of AI and ML analytics for users with minimal support from the IT team. It should also be noted that while the data and analytics is accessible to more users across the business, a modern data platform maintains the same level of security and data governance as a traditional data platform. IT can assign roles to users that determine who can see what data and how much control they have over editing and updating the data sets as well. Finally, there is agile data management. This means having high data availability with the most of the data stored in a data lake or data warehouse. These structures separate storage and compute, making storing a high volume of data relatively inexpensive. Another part of agile data management is elastic and auto-scaled consumption, the ability to only use resources that are necessary. This allows your systems to handle a variable workload and is complemented by a pay-as-you-go model to reduce cost. Use of the cloud is key in agile data management. The cloud model itself already reduces management by removing the responsibility of hardware upkeep. It also introduces the opportunity to use platforms, infrastructure, and softwares as a service to reduce management responsibilities. So let's rewind and look at the structure of a traditional data platform. In this architecture, data moves from its source to a staging layer, where the data is streamlined and goes through some quality checks. It then moves into a data warehouse, which is the central repository for integrated data. Then, the data goes to a MART layer, which stores a subsection of data from the data warehouse and is curated for use by a specific business function or user group. Then, the data is modeled and put into multi-dimensional cubes. The multi-dimensional data models are then used for reporting. And so there are several disadvantages to the traditional data platform. First, the data itself is hosted on-premise and is only structured data and has some connectivity limitations. For analysis, there is SQL querying and limited ETL tooling, but most of the analytics, if not all of them, occur offline on tools like SPSS or SAS. And then the deployment processes are rigid and very manual. In terms of management of this architecture, there is quite a bit of lead time for infrastructure setup, and a database administrator needs to manage the environment. And then, of course, there is a cost associated with data storage. And so now let's look at a modern data architecture. It also starts with a data source layer, but in this version, the data is hosted in the cloud. The data can be structured or unstructured, and this architecture can handle a variety of data sources. One path that the data will take is directly into the data lake, where it moves from raw to process to output as it gets cleaned up, transformed, and tested for quality. The other path that the data can take from the source is directly into automated analytics and machine learning models. And there is an experimentation stage or sandbox to use before scaling up analysis. This layer enables innovation and insights without incurring the cost of analytics at full scale. The analyzed data can be fed into the data lake or can go directly to the next layer, the relational layer, where relationships are formed to create a data model. Then the data model is used for data visualization. Sometimes the relational layer can be skipped and the data goes right from the data lake to the reporting tool. Throughout this whole process, the data is governed using practices like DevOps, data cataloging, and infrastructure as code. So now that we've laid out the overarching structure of our modern data platform, we can drill into the machine learning and advanced analytics layer. Like the larger architecture, it starts with data ingestion and processing, where we bring in the data and prepare it for analysis. We then move to the orchestration step. An ML solution typically has more than one step, with multiple models making up one solution. So an orchestration tool takes care of the multiple steps, passes data between them, and combines them for tracking. So then we have the training step. We build the model based on historical data and update it to take account of new data periodically. This ensures the model's accuracy as behaviors change. Next, we score the model. In this step, we load the trained model and use it to make predictions on what will happen in new or future cases. This can be run for batches of new data, individual examples as they come in, or for what-if scenarios. Then we have the tracking, monitoring, and logging stage, where we do some management of the model. We ask questions like, what models have been trained? Was the training successful? Which version of the data are they trained on? What's the estimated accuracy? Based on new data, is it maintaining that accuracy? Lastly, there is the output and presentation of the model. Outputs need to be presented to users in a wider data context so they can see the whole picture and confidently make business decisions based on the best view of the data. Each of these steps goes through testing and deployment. We practice code management, automated testing, and continuous integration and deployment to optimize the solution's performance and accuracy. And so now I will tie everything together and wrap us up. To summarize, a modern data platform facilitates and manages what are called the 10 V's of big data. The first three, and arguably the most significant, are volume, velocity, and variety. A cloud-based platform allows for more data from a diverse data sources to be ingested at greater speeds. Then we have variability, veracity, and validity, which all refer to the credibility of the data. The auto-scalability of a cloud platform easily handles variations in workloads while reducing overall operating costs. It also can seamlessly integrate with data governance tools that can track data modification and has dedicated layers for cleaning the data through anomaly detection, data quality checks, or other data governance practices. Next, there's vulnerability. As mentioned earlier, a modern data platform maintains the same level of security as traditional data platforms. And then, in terms of volatility, a modern data platform can establish rules for which data is available and make sure that the information can be retrieved quickly once needed. Next comes visualization. A modern data platform effortlessly integrates with data visualization tools like Power BI and Tableau. These tools have a range of visualizations that provide deeper insights than traditional graphs. Lastly, we have value. A lot of the value derived from data comes from predictive analytics using AI and ML. An established cloud-based platform is necessary for these analytics to be run. Additionally, a modern data platform automates a lot of the processes we previously discussed, which increases the efficiency of your work and minimizes the amount of platform management you need to do. The modern data platform is built to ingest whatever data you need, ensure its quality and security, and deliver powerful insights so that you can make data-driven decisions for your business. So we've put up our contact information again. Please feel free to reach out with any questions, and thanks for tuning in.